Right. It's the third short, or at least I'll hope it's short, be short, lecture of the week. This one's on Kohn Sham theory, chapter 5. And of the three videos this week, I think this is the only one that probably everybody ought to take a look at, just because 5 is so dense, and not all of it is critical for your understanding of the work we're going to do in the class. You're welcome to not watch this, and if you're not hearing me, you already know that. All right, so here's Kohn Sham theory. And you'll note that this Kohn name is kind of ubiquitous, right? Owenberg, Kohn Sham. And Walter Kohn is a mid-90s, he's in his mid-90s physicist at the University of California, Santa Barbara. And he is the progenitor of modern density functional theory. He's not responsible for many of the current functionals we use, but the combination of Hohenberg, Kohn 1 and 2, which put density functional theory on a firm physical foundation, theoretical foundation, and Kohn Sham, which we're going to talk about today, which turned it into an accurate theory, were the difference makers. And so he won a Nobel Prize probably about, I don't know, 8-10 years ago for this work, in concert with a fellow named John Popel, who was instrumental in the early stages of wave function theory, electronic structure theory, and is the principal author with his students of Gaussian. So the two of them turned density functional theory not into merely something that was a theoretical interest, but applicable and high accuracy, and that's really quite amazing. And it is Kohn Sham theory, the next thing we're going to talk about. That's the step that turned density functional theory into a quantitatively useful theory in chemistry. It was useful in some areas of physics, but when I was a graduate student, that was 1979 and 1985, people snickered at density functional theory because it was nonsense compared to wave function theory. But as Kohn Sham theory developed and the beginnings of the first really good functionals came about, and density functional theory was more than competitive. So what's Kohn Sham theory do? It fixes the huge error in the kinetic energy function, for example, with Thomas Fermi theory, to grow the 5/3 part. But it comes at a cost. It's no longer formally a density functional theory. It's going to rely on orbitals. We're going to need orbitals to calculate the density, the kinetic energy, and it's going to turn out we're going to use them eventually for parts of the exchange interaction. So we go from that thing in chapter 3 that it didn't matter how big the system it was, it only depended on rho and 3 coordinates. We're going to take a step backwards, and we're going to go now to Slater determinants as a fundamental building block of the theory, which means that for DNA, I got to solve for tens of thousands of orbitals. So you're not going to do that for DNA. You're going to do it for small pieces. Nevertheless, the theory is accurate enough and fast enough compared to wave function theory that it allows us to treat much larger systems. And as I said before, this is a condensation chapter 5. If you take away what I say here, I think you're going to be in fine shape. Okay. So what were Kohn and Sham thinking about? They were thinking about the fact that the kinetic energy functional gave lousy results for the density, for the kinetic energy. I'm sorry, I keep confusing that. It gave lousy results for the kinetic energy. But then they said, Hartree-Fock theory, when you use that, you get a pretty good estimate of the kinetic energy. And all you do is, it's easy to calculate it. If I had orbitals, well, I just take the Laplacian of this orbital, multiply by its orbital complex conjugate, and I sum over all the orbitals. So if Hartree-Fock gets the energy pretty accurately, then maybe it'll do the same for density functional theory. What you do then is assume that you are going to pick up almost all of the actual density functional kinetic energy using a term like this, and there'll be a small correction, and you're going to fold that into the exchange correlation potential. What you then get out is you're going to solve for a set of Kohn-Sham orbitals and eigenvalues. This will look familiar. It'll look just like Hartree-Fock theory, but the difference is the potential is a little simpler. it is just for each electron, a kinetic energy plus the Kohn-Sham potential. And that multiplies by the orbital, and then you do that to the orbital, you get an eigenvalue. All right, well, this looks like a mess. But here you are, you've got the Kohn-Sham orbitals, and there's the kinetic energy. And you got a total energy here, which is the Kohn-Sham kinetic energy, which is not exact because this is the exact kinetic energy for a Slater determinant, but that's not the density we necessarily have. It's got a classical repulsion. It's got an interaction with the electron and the nuclei, and then it's got the exchange correlation energy. But the new thing here is the old exchange correlation energy, where we thought of it, was just the difference between the electron repulsion and the Coulomb classical term. But there's a secondary piece here, which is the difference between the actual kinetic energy functional with the density and the Kohn-Sham kinetic energy with the given density. And I should make explicit, this is set up in such a way that if you had the exact exchange correlation energy and potential and the Kohn-Sham potential, then the orbitals, the Slater determinant you get, would yield the exact density. So this is not a mistake, those are the same density. Okay, you see the pieces that are in here. Here are ones we've seen before. There's the kinetic energy with the orbitals, there's the classical repulsion, there's the electron nuclear attraction, so it's right here. There's the classical repulsion, that's this term. But then there's the magical EXC of rho. That's where all the magic happens. That's what turns this into an exact theory. Furthermore, the Kohn-Sham potential that determines the orbitals looks like this. It's the repulsion with all the electrons. There's the density. So that still has self-interaction error. So the electron repels itself. It still has no correlation. And I'm blanking on the other thing, but I'll think about it in a second. Here's the attraction to the nuclei. Oh, and it doesn't have an exchange. Here's the attraction to the nuclei. And here is then the piece that's added that is going to fix it all up. That's going to put back in exchange, back in correlation, back in the self-interaction correction. And it is defined as the functional derivative of EXC, whatever that is, with respect to changes in rho. So that's what you need. If you had this exactly, if you knew exactly what EXC was as a function of rho, and could take that derivative, you'd have VS. You would go back and solve the Kohn-Sham equations with VS. That would yield for you the exact density. You would plug it here, and you'd get the exact energy. Okay, so this is a translation. The Kohn-Sham system is the same density as the exact result, but with non-interacting particles. And that's under the assumption that you know what the exact exchange correlation energy is. VXC adds the magic to turn Hartree-Fock-like equations. Look, this is actually simpler than Hartree-Fock, right? We had exchange and Coulomb terms in here. It's really, and attraction nucleus. This is really simple. It adds the magic to turn Hartree-Fock-like equations, which we know give poor dissociation energies, for example, into orbitals that yield the exact density and the exact ground state energy with this density. But only if we had this. Oops. Only if we had this exactly, right there. We need to know the exact exchange correlation energy, and we need to know its exact functional derivative. So there are some comments that follow, but let me first make several. One is, we don't have the exact EXC. In the chapters that follow, we'll start to look at approximations to it. We'll look at a simple system where we know what the exact result is, but we do not have the exact EXC. Furthermore, since we don't have the exact EXC, we don't have its functional derivative. All we have are approximations. So the key is here that when you do density functional theory, although there is this promise that if you had the exact VXC, the orbitals would yield the exact density and the exact ground state energy with this density, the answer is we never get that because we don't have the exact EXC. And what that means is the variational principle is actually no longer valid. We could get two energies here from different functionals, and we would not know which one is better than the other because of the variational principle, because in effect, by not knowing the exact EXC, you're not using the exact Hamiltonian. And the variational principle is all predicated on the exact Hamiltonian. So that's not a real problem for us here because of the accuracy of the method, but I want to show you that what's happened is we use the variation principle a lot. We think about it hard, we minimize energies with respect to the orbital variations, but in the end, it's not truly variational because not knowing EXC is the same as not knowing what the exact Hamiltonian is. Okay, so here's some other comments. VS is local. It means it's really easy to calculate. It only depends on where you are. I wouldn't worry much beyond this, but it just says that's really easy. Unlike the exchange interaction, which requires an integral over your orbital over all space. X and C are different for Hartree-Fock and Kohn Sham. In part, X, because the orbitals are different. Correlation, because since the orbitals are different, there's slightly different definitions for correlations. I wouldn't worry beyond this point. Do the orbitals mean anything? That really depends on what group of people you sit with. The fight still rages. We're not going to settle it. I would argue that from a chemist's point of view, and for physicists too, the orbitals are qualitative guide in the same way that they are for Hartree-Fock. In a way, the Hartree-Fock orbitals don't really mean anything anyway because the overall wave function is correlated. Okay, so is it a single determinant theory? That's not terribly useful for us here, but I'd be happy to chat about it. I guess the answer is the Kohn Sham certainly relies on a single determinant, but there are places where we really can't represent the density as a single determinant. So unrestricted Kohn Sham, so you got odd number of electrons, or you've got an even number, and you're dissociating, it dissociates bond better. After this, after 5.35, read if you want, chat with me. But in the end, these are all sorts of details that aren't germane to the class for almost everything everybody's going to do, but I'm happy to chat if people are interested. So I'm going to stop the share and stop the recording.